Hello everyone. Once again, I would like to welcome all the viewers to this online class that is conducted especially for the class 10 students. Last class we are done with probability. Today we are going to do circles from maths textbook under the MBOSE syllabus. Let us start this chapter. First of all, we will understand what do we mean by circles. In understanding this term, we will consider this plane of this board. Let us take one point which is on this plane, and let us fix this point, and let us take any other point which is on the same plane. Suppose this distance of this fixed point from this point that we have taken on the same plane, suppose it is 10 centimeters. Then we will put a condition on this point, that is, it can move along this plane in such a way that its distance from this fixed point will always remain 10 cm. Then if we put that condition on this point, then along which path can this point move? It cannot come closer to this point, otherwise the distance will not be 10 cm anymore, and it cannot also go further from this point. Then this point, it can only trace when it is giving this condition to this point, that is can move only keeping the distance to be 10 cm always from this fixed point. It can move only along this path, so that when this point reaches here, the distance of this point from this point will still be 10 cm. And if it moves along this plane, it can move only along this path. But when we draw it properly, suppose we consider this plane of this paper. Suppose we fix this one point here and we take any other point. Then if we put a condition on this point that it can move along this plane of this paper in such a way that the distance will always remain this much, then this point will trace this type of path. So this path traced by this point in the plane under this condition, this is called a circle. So if you draw properly, it will be like this one. So let us define a circle. So definition: a circle is a path traced by a point in a plane in such a way that its distance from a fixed point is always constant. This is the fixed point, and call this fixed point to be the center of the circle. And in general, we can have this distance to be of any measure. It may not be 10 cm always, but this distance, which is always constant, this distance is called the radius. So this is a circle. So when we talk about circles, we always talk which is in a plane. We will see how many cases will arise when we consider a line and a circle. See? Suppose I draw this circle, and the center, suppose it is here, and this line. As you can see, this line and this circle, they have no common point. This line does not intersect the circle at any point. So this type of line, suppose I call this line to be L. This line L is called non-intersecting line with respect to the circle. This is the first case that we have when we consider a line and a circle. Let us have the other possibilities that we can get. Suppose I draw this circle again, and suppose the center is somewhere here, and I draw this line. Let me call this line to be L. As you can see, this line L is intersecting this circle at 2 points, and these 2 points, they are distinct. So such kind of line which intersect a circle at 2 distinct points is called a secant of the circle. So here L is called a secant of the circle. You can also have another case. Suppose we have a circle and suppose we consider this line. This line here is intersecting at these 2 points. If I call this one to be A and this one to be B, and here this line L is intersecting this circle at exactly 1 point, namely this point right here. Suppose I call this point to be P. As you can see, this line and this circle, they have exactly one common point. So this is different from this and from this case. So this type of line is called a tangent to the circle. And this point, where this line L touches the circle, this is called the point of contact. So here L is called a tangent to the circle. So these are the only possibilities that we can get when we consider a line and a circle. But here we will discuss more about this line, which is called a tangent. So let us have a look at some properties of a tangent to a circle. Let us have a look at some properties of a tangent to a circle. We know that a tangent is a line which touches the circle at exactly 1 point. Now, first of all, let us consider this circle, and we take, suppose this is the center, and we take any point which is lying outside the circle. Let us draw all possible lines that will intersect this circle. So let me draw all these lines. As you can see, from these 4 lines, as you can see, these 2 lines here, they intersect this circle at 2 distinct points. And these are the only lines, this one and this one at the bottom, that touch the circle at exactly 1 point. So from here, what can we say? How many tangents can we draw to a circle from an external point? There are only 2 tangents that we can draw to a circle from an external point. So this is the first property that we are discussing. So we have this, only 2 tangents can be drawn to a circle from an external point. So let us have a look at some more properties. And here we have this point P to be lying outside the circle. Let us take the case when this point P is inside the circle. So let us draw a circle. Suppose this is the center, and we take point P anywhere inside the circle. Then how many tangents can we draw to this circle passing through this point P? So let us draw all possible lines passing through this point P. All these lines. As you can see, this line is passing through this point P and it touches the circle at two distinct points. And these lines, these other two lines also, they pass through point P, but they intersect the circle at two distinct points. So all the three, they are seconds to this circle, but they are not tangents. And if you draw all possible lines, you will see that if they pass through P, they will always intersect the circle at two distinct points. So from here we can see that no tangent can be drawn to a circle passing through a point which is inside the circle. So let us write this second property that we have. No tangent can be drawn to a circle passing through a point lying inside the circle. Now let us have a look at the third case when this point P is not outside or inside, but when it is lying on the circle. So let us have a look at that third property. Draw a circle and we take any point P which is on the circle. Suppose this is the point P. Then here also the question that comes is that how many tangents can we draw to a circle passing through a point P lying on the circle. So let me draw this one line which is passing through this point of the circle. This is a straight line. And let me draw all possible lines which is passing through this point P which is on the circle. Let us have a look at only these three lines. As you can see here, this one line from here, it is touching this circle at only this point. So this line, if I call this line to be L, this is a tangent to this circle. But all the other lines passing through this point P, they will always cut the circle at two distinct points. This one also is cutting the circle at this point, and here which is different from this point. So from here we can conclude that through a point lying on the circle, we can draw exactly one tangent. So this is the third property, and we have one and only one tangent can be drawn through a point lying on the circle. So these are a few properties that I want to discuss that we need in this chapter. Now we will try to do some theorems that we need to proceed further. Now we will do this theorem which states that a tangent to a circle is perpendicular to the radius through the point of contact. So this statement, we will first draw a diagram. So it is given that a tangent to a circle. So we have a circle and a tangent. Suppose I consider this tangent. Suppose we consider this tangent which is touching this circle at this point. Let's say this point to be P, and suppose this is the center of circle. Then the radius through the point of contact is that radius which will pass through this point of contact. Let us call the center to be O. Then this theorem states that the tangent and this radius through the point of contact, they are perpendicular to each other. This is what we have to prove. So the proof, it is given that given a tangent AB and intersecting the circle of center O and P. We have to prove that the statement of the theorem states that the radius and the tangent, they are perpendicular, so we have to prove OP is perpendicular to AB. Now, in proving this theorem, first, if we take any line and any other point which is not lying on the line, then the shortest line segment between this point and any other point on this line will always be the perpendicular. So this will not be the shortest line segment between this point and any point on this line. The shortest line segment will always be that line which is perpendicular to this line. And here also, in order to show that this OP is perpendicular to this line AB, it is enough for us to show that OP is the shortest line segment between this point O and any other point on this tangent. That is what we are going to use to prove this theorem. So we are trying to show that OP is the shortest line segment. So it must be shorter than any other line joining O to any point on AB. So let us take any point on AB and suppose we call that point to be Q. And this is the construction that we are making, and we join this OQ. We join this OQ, and this line will meet this circle at this point. We call this point to be R. So the construction here is we join OQ. First of all, that we are taking that point Q, so we will mention that we take Q on the line AB, which is other than the point P, and we are joining. We join OQ meeting the circle at R. So this is the construction that we are making here, and as you can see from this construction, OQ, it is equal to OR plus RQ. So from the diagram we have OQ is equal to OR plus RQ. And here OR is the radius of this circle, OP is also the radius of the same circle. So in place of OR I can write OP, since OP is equal to OR. So from here we have that OQ is greater than OP, because to OP we have to add some other quantity so that the whole will be equal to OQ. So from here we have that OQ is greater than OP, or we can write this as OP is less than OQ. So what can we say from here? We can say that OP, the line segment OP, is shorter than the line segment OQ. And this point Q, we can take any point on this line AB other than P. If we take this point Q to be anywhere other than P, we will still get OP to be shorter than OQ. So from here we have proved that OP is the shortest line segment of all the line segments joining the point O and any point on the tangent AB. So hence from here, OP is the shortest line segment joining O and any point on AB. So hence we have the proof. So hence the proof. We can also have the converse of this theorem to be true. So that is the next theorem that we're going to do. That is, we are trying to prove the converse of this theorem. So next class we are going to prove the converse of this theorem. So for now we will stop here. Until then, we will see you next time. Thank you.